All right, so I'm here. I'm a confused academic, right? So I've been doing database stuff for a while. I've been in the field for over 30 years. And I don't think there's been a more confusing time than now, so it's really fun. So I'm going to talk about that. So what I'm confused about is storage, and I'm also confused about like layers. Like how should these architectures look? Talks today have been great. There have been different layers everywhere. And so my question is, like, what should we be doing about that in academia and also kind of as a field? So what I'm going to do is talk about sort of just like why I'm confused, talk about sort of my academic naive point of view of what's been going on in two worlds, the systems world and the database world, and also sort of the clouding that's coming along from what's happening in the cloud. And then I'll talk a little bit about the system that I'm working on at UC Irvine as a context for trying to get unconfused and doing some experiments, and I'll talk about what we're doing. I'll sort of share my questions, and then your assignment, your homework is to send me email telling me what the answer is and what I should be teaching my students now that we're in this confusing world. So everybody send me the answer, and I'll accumulate the answers, and the majority will win. And also, yeah, request for input kind of at the end. So obviously, big data, I don't have to convince you. I'm from the VLDB world, so I'm only used to dealing with very large data. You guys are the XLDB world, so the X is even more. What I like about this is I don't have to apologize anymore at parties for being from the database community, right? So databases are now cool. Everybody's doing data stuff. And in our Asterisk project, we're basically building a semi-structured data management platform. Okay, so what I want to do, since I'm an academic, is I teach about like what's happened. Go back a little bit in time and think about sort of dealing with databases and dealing with data in parallel. So we're going to actually go back to 1979, like before I was even in grad school. And Dave DeWitt, one of my colleagues from Wisconsin for a number of years, was working on parallel databases, working on how do we manage like data, how do we do query execution, and really scale it up in parallel, like really scale it up in 1979, right? So this is actually the picture from a report that he was working on in this project. You've probably never heard of this project because he describes this as the failure that got him tenure, and I'll talk about the failure part of that. So basically what he was looking at was building a parallel database using sort of the new emerging storage technologies, which happened to be CCDs at the time, and having a bunch of sort of query execution engines and running in parallel against that data. So essentially think sort of prehistoric shared disk architecture. And so what happened was, a lesson from this, which sort of got him tenure, was it turns out that like brute force doesn't necessarily win. Right, so you've all heard about the Wisconsin benchmark probably, and that was actually motivated by doing a comparison between his approach to doing parallel databases and sort of regular approaches like the then innovative Ingress system from Berkeley, which had things like indexes in them. And basically when he measured, how could he compare to a sort of a single server of the day database engine with his parallel technology, he lost the battle. And the reason was sort of brute force doesn't win over smart data structures. So we'll come back to that sort of later on. But sort of remember that picture and remember that architecture, and I'll actually have it for you again when we need it later. Okay, so then there's another part of history, which is I sort of grew up in the era where it was really fun. You'd get like 3 people up on stage. One person would like shared everything, one person would like shared disk, and one person would like shared nothing. And there'd be a big battle, and they'd call each other names, and they'd call each other's mothers' names, and so on. And they had to sort of sort this out, like what's the right architecture? Right, so we've also sort of been through this architecture where there's a lot of alternatives for like how should the data, the state, this large, potentially persistent state, be interacted with by the query processors, and how should that work? Who should own what? How should it be partitioned, and so on? And so there's the shared everything where everybody can access everything in shared memory, which is now sort of our multi-core. There's the shared disk, which is looking familiar again. And then there's also sort of shared nothing, which is what you see under the hood of pretty much any parallel database system. And this is all sort of being sorted out so people in the 1980s knew what they should do in terms of their architectures. So that brought us to sort of in the database world. Everybody knows the story. Teradata is like hugely successful. Enterprise data warehouses have had this VLDB or XLDB problem for a very long time, right? So back in the 1980s, this kind of got sorted out, like once and for all, we thought, right? So pretty much shared nothing parallel databases won the day. Most of the scalable databases ended up following that architecture. Teradata was dominant for a number of years. They still are. But in the early 2000s, along came a number of other players sort of wanting to be the next Teradata and had these startups sort of taking and orchestrating open source things to create a Teradata-like architecture with shared nothing. They were all successful in the sense of being acquired by, for at least hundreds of millions of dollars, if not billions of dollars. So there's obviously sort of a huge thing happening here. And it's all based on the shared nothing architecture. If you look under the hood, the layers are clear, right? We all know how to build one of these things. You build a really good storage manager that has indexing and manages records, and maybe we slice them, sort of vertically instead of horizontally now, rows or columns you choose. On top of that, you build a data flow execution engine, right? So the sort of the big data companies are now adopting data flow techniques. The database systems have actually had these techniques under the hood for 20 or 30 years, right? And we've thought about that in CACM and elsewhere. And then on top of that, there's a compiler that takes a high-level language because we've also had people who got bored more quickly with writing programs, and we've given them SQL or other high-level languages, and we compile that into our world, right? So basically, we've said, we can solve parallel big data, but you have to learn our language, and you can only talk to us through our language. And so we have that architecture, but it's pretty clear. I can teach that. I know what to do, right? One storage manager per machine, upper layers orchestrate, one way in, one way out. And that's, in some sense, the result also of the direct lesson, which is if you don't have a good storage manager at the bottom, parallelism is not going to win the day. So this is kind of the standard, the gold standard, if you will, for what does a parallel database look like. So we've heard the story, already heard it in the talk today. I won't sort of go through it, right? So Google sort of went on this adventure to deal with large data that wasn't relational and built a wonderful foundation. They built MapReduce and the Google file system underneath that for storing large amounts of data and not having to think too much about parallelism when you're programming against that data. And so we got the Google file system and MapReduce. And the open source community read the papers and went, those are really nice design specs. I think we can build that. Right, so Yahoo and Facebook and others read those papers and built out sort of what is now driving kind of the non-Google sort of big data, or at least has been for the last few years. So we had HDFS instead of GFS, Hadoop MapReduce, declarative high-level languages. So instead of the Flume Java stuff, we have sort of Pig, we have Hive, and most people using those rather than using MapReduce by hand. And then we also kind of on the more operational big data side, Compaq had nonstop SQL in the database world. In this world, we also have these NoSQL stores, which are also doing big data, sort of a different kind, of a more small operations kind. And when you look at the stack looks a little sort of more open, more flexible. At the bottom of this stack, there's a distributed file system. So that, sort of the answer to where do you put your persistent bits is in the distributed file system. On top of that, you could build a key value store, or you could have something like Hadoop MapReduce. Because you don't want to write MapReduce assembly language programs, you can have something like HiveQL or Pig, or pick your favorite scripting language on top. So that's sort of how the big data systems world has shaped up. Looks pretty different than the database world, but some of the same principles apply. And it's also shared nothing, although it's kind of a sort of a shared disk on top of shared nothing abstraction with the HDFS file system. Okay, and if you look kind of at the platforms today, this is just a sort of a small subset of all the big data analysis platforms. There's Microsoft has something that looks like this. We've sort of self-servingly put the Asterisk platform in there. There's the Flink platform in there. Now it's not named Flink in that, but it's sort of the descendants of that. You sort of see all the non-sort of only SQL-based ones represented here. We won't go through the details, but at the bottom of lots of those, we have HDFS and GFS, right? So we have kind of this big distributed file system sitting at the bottom. And as a database person, I'm confused. I'm going, really? Is that what we want to be doing? Is it now the case that we need to or that we should be sort of relegating persistence to a distributed file system and building our database layers on top? There's a lot of that going on these days. But a lot of those platforms are really sort of scanning all the data and doing processing, and we'll come back to that. So remember history, right? So we looked at direct. Well, that's shared secondary storage, and that's scan-based query processing. And that's what a lot of those architectures are doing. And the last time this was experimented with, it didn't end well, right? So the question is there something really different today? Or are we on a path of kind of rediscovering what we could learn if we look back at sort of the early days of parallel databases? And I'm confused, I don't know, so I'm raising the question. So you can sort of help me decide. Okay, one more bit of history. One of the papers we require our students to read, because it's interesting historically, is a paper that Mike Stonebreaker, my old advisor, wrote, sort of operating system support for database management. This is also written a very long time ago in the early Berkeley Unix days. So none of the lessons sort of directly apply, but there's interesting analogies maybe to be made. Right, and this dates back to 1981, so not quite as far back as direct, 2 years later, sort of looking at the Ingress experience, sort of building a database system on top of Unix. And so this, sort of the summary of the paper was, well, you know, we're going to look at sort of these services, like how do operating systems manage buffering? How do they deal with files? How do they schedule? How do they synchronize? You know, sort of how does all that work? How does that compare to what databases need? And the conclusion was, well, not so well, right? And so this kind of set the whole database world, not the paper necessarily, but people discovered these for themselves and set off on a path where they were sort of reacting to this by taking over a lot of that. Database systems had their own way of dealing with files. They'd look at the sort of the whole disk as a device and do all their own storage management, do their own buffer management, do their own thread management, and so on. And a lot of the systems sort of do most of that rather than delegating it to the operating system. That's what was happening back then. The question is, you know, where should we be today? Should we be delegating all of this to HDFS or GFS or other sort of file systems and building on top, or you know, do we still need to do our own thing if we're dealing with the persistent, the major state that we're stuck with in the world of big data? Okay, and then the other thing that you can see if you're kind of looking at the space and wanting to figure out what to work on in a university is, you know, if you ask anybody what their IT shop looks like, it looks something like this, right? There's a little bit of everything. You know, maybe the MySQL, and that didn't work so well, and so there's some, you know, NoSQL stores from different projects, and, you know, something was too slow, like MySQL, and so there's Memcache, and, you know, we rolled in Hadoop because we wanted to analyze our data, and then our programmers got annoyed with us, and so we gave them Pig and Hive, and we've got this all sort of bubblegummed and bailing wire together. And so that's also kind of unfortunate. There's an awful lot of moving parts, and I kind of like the Google story that we heard right before lunch about wanting to reduce kind of this whole mess and be able to deal less with that. So it is kind of a mess, and so that's just an observation. Okay, so what are we doing at UCI? And then I'll come back to my confusion and sort of questions about storage management. So we looked at this back in about 2008. I sort of rejoined academia, and we had to figure out something to do. I had, you know, been at a startup, or not a startup, but a company that was acquired by Oracle, and so I had to check my code base at the door when I left, and so I needed to build a new code base. And so we set out to say, if we had a shared nothing cluster, and we have the knowledge, the lessons from the database community about how to process things efficiently and how to partition data and do data flow processing, like if we were building that stack for something like Pig or Hive, and we wanted a more flexible data model, and we knew we were going for a high-level language, what would we do? And so we said, well, we would take ideas from semi-structured data management, ideas from parallel databases, ideas from the Hadoop world, and the way that they deal with data, the way that they deal with storage, and the way that they deal with sort of data flow processing. We'd mix them all up, and we would try to build something that has sort of a slightly more, maybe a more sensible architecture if you believe our architecture, or not if you don't. And so we said, let's build a big data management system, right? So everybody's building big data analytics. Big data analytics is, my data's in a file system, I'm going to scan it all and do something really cool with it, but I'm going to have to read it all. And so that's a great thing. We need a lot of that. We wanted to ask the question, what would a next generation data manager look like that actually owns the data, might index the data, might know how the data is laid out so that if you ask a query, it can subset the data in a way rather than having to scan everything. And so sort of our wish list, or at least our revisionist sort of history wish list, was a big data manager ought to have a flexible data model. It ought to have an efficient runtime. So as we've already heard, and sort of the community is realizing, MapReduce is not the perfect execution engine for query processing. And so we wanted to have a better one. We wanted to have a full query capability, right? So you can get full query capabilities out of your scan all of your data solutions today. You can't get a full query capability out of a NoSQL store. If you have questions about multiple collections of data, that's for your program, your client to write, not a query language. And we thought, well, that's, you know, I want my data and I want to eat it too. I don't want to have to either store it or query it. I should have both. The cost of my data processing should be proportional to what I'm asking, right? So if I have a little question, it should take a little amount of time to answer that question. I shouldn't have to start a job and scan all my data. Databases have known how to do that for years. Let's bring that knowledge to bear on big data. And then while we're at it, big data comes from data flowing in constantly. So let's think about this sort of streams of data are coming in and being persisted world. How do we design a system to sort of deal with some of the continuous ingestion? And then also there's a bunch of data types that are important today. Location, 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 everybody's somewhere and checking in. And so we need to deal with spatial data, at least simple spatial. We need to deal with textual data and do approximate things. We need to deal with temporal data because times are very important. We've got to have sort of built-in good support for that. So that was kind of our list of things to put in the system. And so what I'm going to do is talk just a little bit about what's in the system, just to kind of set the context, and then talk about sort of how we're storing it today, what we're going to do to hedge our bets, and why I'm confused. Okay, so we have a data model, right? So the other thing which is fun as an academic is I grew up in the relational era, and the question is, what's the data model? The answer is relational. The question is, what's the query language? The answer is SQL. And now we're in an era where you can actually explore other solutions. And so because we were starting a new project and everybody had their own data model, and we didn't want to feel left out or miss out on the fun, we designed our own. So we have a data model which is basically inspired by JSON, which we worked for many years and previously in sort of my former life in industry on XML and XML query processing. And so we sort of looked and went, okay, everybody's tired of these pointy brackets. JSON's catching on. Let's take a look at JSON data. Has nice nesting, has nice openness. If you had a data model for that, what would it look like? And so the data model in our system is kind of along those lines. And so you could create types. If you know a lot about your data, you could write a description saying, I've got an ID and an alias, and I have a nested record, which would be forbidden and relational. Maybe I have a set of friend IDs and a list of employment records. So we can have a data model that supports richer types, sort of more document store style data types. And they can have other data types in them. And then if you want to store stuff, you'll create data sets of that. So we basically just sort of said, what's the obvious data model if you take JSON and some ideas from object databases and build a data model for that. And so that's kind of what's in our system in terms of describing your data. And then we also have this notion of sort of wanting to be flexible. And so if all you want to say is that, that's fine. You can say the same thing, you can say that, you can store your data, write the same queries you could have written before. And so we have a system where you get to decide how much of your data model you want to disclose and how much of it you want to hide in the application program. As database people, we might advise that this is better for the application developers, but if you really don't know, you can build that and you can write the same apps. And so we have there's a grayscale. You can turn the dial from 1 to 10 or set it to 11 if you really want to lock down your schema and sort of be more relational. We have indexing, right? So unlike sort of a big data analytics system, we actually are managing this data. And so you can index this data. We support B trees and R trees, and we support text indexes. And we also support a notion kind of shown in the middle there as what we call sort of external data sets. And I'll talk a little bit more about that in a second, where you can basically say, I want to pretend that this data is in my system, but it's not in my system. It's actually, for example, in my local file system, or it's in HDFS, or it's in Hive. And I'll come back to that. And then we have a notion of something called data feeds that I won't talk about today because I want to focus on storage. So this is, again, just setting the context. And then we have a query language. So if you want to ask questions about, like, who are the active users and what countries are they in, I won't go through the details, but you can write queries. The queries can actually go over multiple data sets. So here I'm going over my users data set and my access log data set and doing some aggregation that I won't sort of bore you with the details of, but just to give a flavor for the kinds of things we want to be able to do on the storage that I'm confused about. So that's a quick overview of kind of the user experience for Asterix. So let's sort of move down a little bit to the more relevant, which is what does it look like as a piece of software, and what are its layers, and how does it store and manage its data? And so kind of at the top, we look, like you've got in a normal system, data can come in, you can load it in, either sort of in a batch, you can feed it in continuously with our support for data feeds, which I can tell you more about offline. And so those are two ways of getting data into the system. You can also write Asterix query language inserts and updates and deletes to get your data kind of manipulated in the usual sort of database kind of way. So you can also get data in and out of the system that way. Queries come in, and we're kind of working on sort of data pub sub in our current research. You talk to something that looks a lot like the layers of a parallel database. So you talk to the client interface, there's a query compiler, and there's metadata management so that we're keeping track of schema for that data for which schema has been pre-declared, or the parts of the schema has been pre-declared. We have a data flow engine called Hyrax, which is not MapReduce based, can do some tenthing in between things, but is also focused on pipelining and being efficient. Essentially, this looks like what would happen if you kind of formalized the runtime underneath the hood of pick your favorite parallel database. The innards of DB2 or the innards of Teradata, we have a data flow engine that's arbitrary sort of DAG executor that's inside our system. That sits on top of storage for data sets and feeds into data sets, which are based on LSM trees, which I'll talk about next. But notice that we have these nodes, and each node has some locally attached storage, has kind of a full data manager, and then sort of it's orchestrated. Oops, before I switch. It's orchestrated by sort of the query execution. So a query will run on multiple nodes in a parallel data flow kind of way, as you would expect if you were building a parallel database, but it has this more open model and can also support data that's not stored in the system. Okay, so what's on disk? So on each node, there's a bunch of disks, each of which can store a partition of your data. And we're using what's now popular, which seems to make a lot of sense for ingesting data quickly, log-structured merge tree, component-based log-structured merge trees for our storage. And so as new data comes in, since we want to be able to take in data quickly because we're amassing big data, the new data comes into a memory component. Memory component sort of exceeds some threshold. When you decide that you're sort of tired of having that as a memory component, it's too big, it gets flushed to disk. Whoops, sorry, pushing the wrong buttons here. It gets flushed to disk and becomes a new on-disk component. And then over time, you might take some of these on-disk components and merge them. And there's work was done on this a number of years ago. This is now popular inside HBase and other kinds of systems. And so we're doing that, except we're kind of doing it on steroids, which is to say, that's how we store our records. That's also how all of our indexes work. And so everything in our system is LSM-based. It turns out to make life simpler when you're building crash recovery, not having to sort of read and understand all of Mohan's papers again. You can build things that's a little simpler, not completely simple, but it simplifies the transactional, kind of the atomicity that you'd like to be able to deliver. So that's kind of why we adopted this. It's also great at bringing in data quickly because you're basically sort of taking your data in memory and then writing batches of data and getting sequential write throughput. All the things that were motivators for LSM. We have LSMB trees, LSMR trees for dealing with spatial data, and LSM inverted indexes. And so if you look at our storage, you have a bunch of shared nothing nodes, and on each of those nodes, they're doing this kind of storage management. Okay, so what does the distribution look like? Basically, you can partition your data however you want, as long as you want hash partitions on primary key right now. So that's you have that wide range of options. It's shared nothing, and the data is stored locally, right? So we're basically asking the question, if you're building a data service like for deployment inside the cloud, what would that look like? And our secondary indexes are all local, which is to say a secondary index only contains information about what are the corresponding primary keys on the data on its node. And so we're able to keep them transactionally consistent because we never have to cross node boundaries to do transactions. And then we also support external data sets. And so you can basically make your favorite Hive tables, which are in HDFS, look to us as though we own them, and not own them from the perspective of managing the life cycle of the data, but own them from being able to query them. And so we can also do scans of your favorite data in HDFS. We've also added support for indexing those with a sort of a client-managed life cycle so that we can index that data and update those indexes periodically when you tell us it's time to look again. So you can actually index that data and get your short answers on your little queries over your external data if you would like to. The index partitions, what we do is we sort of interact with the where's the data manager inside HDFS, and we try to, if we're sort of co-located cluster-wise, to put the index partitions similarly with the data so that there's not a lot of distribution of execution that has to happen, not a lot of communication. And we developed this external data set feature for a couple of reasons. So we started out just managing our own data. We were talking to some, one big web company, and they're like, this whole fast query thing sounds great. Please tell me I don't have to put my data in your system yet. We're like, well, the good news is we can actually process queries on your data. The bad news is if we don't own it, we can't index it, and we can't scan it. We have to scan it. And so we basically added that support for that purpose. And that company also said we're sort of out of space. We can't make another copy of our data. So even if we could, we wouldn't. And so this allows you to use our language and our processing over that. So that's another kind of storagey thing. We're working on data replication, so work in progress, data replication. We are doing it the database way, right? So we're not relying on HDFS to replicate data for us. We're looking back kind of at the history of what are good ways of doing data replication. We're using a technique called chain declustering, which has sort of some nice load balancing and recovery properties. And we're doing log-based replication rather than doing kind of block-level replication. And so when a node is making updates, it's shipping log records to its friends. It's whoever its designated friends are, and they're kind of in a ring structure. And those friends are responsible for also being able to get those log records back if necessary. We're not trying to keep active copies on 3 nodes. We don't actually want the kind of the overhead that would be required to do that. And so we're basically just making sure that a couple of other nodes are able to recover the data if necessary, but not ready to run a query on it right now. Okay, so that's our approach to storage. There's an alternate approach, which is just let HDFS do it. And kids today think that might be the right approach. And so we're also looking at sort of hedging our bets. And so what are we doing there? Well, we started out doing in-place indexes and in-place data storage and moved to LSM. And so we had sort of rejected HDFS as a possible store in the early days, partly because of, sort of it was not stable yet at that point, and partly because we were trying to do updates and HDFS didn't like that. Now that we've adopted an append-only architecture, we could possibly put our LSM storage on top of HDFS. So we're doing a let's see what happens exercise right now. And that might make IT managers feel more comfortable using our system because they're like, well, I know the file system is the one that I know how to manage and trust. This is another possible path to replication and high availability, and we're going to be able to do some interesting experiments. So, one question is the right answer today that the distributed file system should manage the data, and the database system on top should just let it? I actually don't think so, but this will give us an opportunity to explore that. So we can kind of revisit, sort of the fast forward 30 years Stonebreaker paper going, okay, are the file systems of today, the big distributed ones, like the right answer for the big distributed big data systems or not? And I think probably not, but it'll be fun to see. So we can do a bake-off of distributed record management versus distributed file systems. We can ask, does HDFS do a pretty good job if we sort of manage ourselves in a shared nothing-y kind of way? Will we get a shared nothing-y kind of partitioning or not? Okay. The other point of confusion, which is much more confusing in a sense, and we've seen lots of different, sort of large real architectures here, is we have the cloud, right? And so there's always this question, what about state? What about my data? I can move my computation. I can scale up my computation by a factor of 3. I can't just scale up my data by a factor of 3 because, 5 minutes from now I need to run something. And so, this sort of seems like it's an argument for sort of the big distributed sort of shared disk / sort of attached storage model being much more relevant today, and I think it probably is. But sort of what do we do about this? How do we deal with our state in the world if I'm deploying inside something like sort of the Google sort of service, maybe the Google persistent disk notion, which I need to learn more about. Performance implications of all this would be interesting to look at. And so I think there's a lot of open questions about, sort of revisiting kind of the shared everything, shared disk, shared nothing in the modern world. Okay. Just a little bit of what are the kinds of use cases that we're after in our project. We've been sort of playing with colleagues that are doing behavioral science data analysis, social data analytics, cell phone analytics, education, sort of MOOC analytics, power usage monitoring, kind of a sensory application, doing social data for the purpose of public health, and also sort of managing logs from large computing clusters that are reporting what's going on. And actually, time won't permit, so we won't look at any of those. I meant to take that off the slide. I knew I wouldn't have time. So where are we? So what are we doing at UC Irvine? Basically, we spent 4 years of your tax dollars building this system. It's about 250,000 lines of code. We've just moved it into Apache. We're incubating in Apache. So there's now the Apache *DB project, sort of has the cool stuff that I've alluded to, and has its own sort of shared nothing approach to storage that's somewhat database traditional, but also based on log structured merge trees, and lots of questions about whether, what alternative architectures there might be. So it's, a system that people could use to actually do some interesting big data things. It's also hopefully going to be a playground for exploring some of these things. For more information, sort of on the slides, you can find out more about sort of the code base, the whole project, at our main page. At the bottom, we're thanking our sponsors. And I have 10 seconds in which to say, for more, we're the new kid on the block. Check us out. All right, done 5 seconds early.
Thank you, Mike. Any short clarifying questions before we bring up Theo? Now, again, there's lots of interesting questions that Mike raised, so I'm going to save some of those for the panel.
Or email
so
the
we'll get a
answers
chance.
to me.
No, we want them on the panel. We want this on film. Go ahead.
Sure.
My name is Ron Hu. I am with Huawei Technologies. Just now in your presentation, you mentioned that you want to make the cost model proportional to the task. This is a great goal.
Right.
And you also mentioned that you want to build secondary index on HDFS. Are there some relationship between these two?
Yeah, so cost proportional to the goal means if you ask a small question, we should be able to exploit an index and just subset the data and give you an answer without having to scan all of your data. The secondary indexes on HDFS thought is a crazy experiment, in my opinion, but we're doing it, right? So we're basically saying, we've got our own shared nothing storage. Right now, all of our secondary indexes are local storage, sort of traditional modulo being log structured. Now that they're log structured, we could slide, how hard can this be? We've been working on it for about a year. It's harder than it sounds. You could just slide HDFS underneath our current log structured solution and see how that performs, right? And if it's just as good, then maybe we should have started with HDFS. I don't think that's going to be the case. I think we're going to see that it still makes sense for data managers to actually be a little bit more owning of their data. But it's an experiment we're going to do. The glitch in the experiment was we moved from updatable, like B trees, updatable R trees, updatable text indexes, to creating a log structured version of that using those as components. And log structured indicates that it's append only, but since we started with updates, we cheated a little bit, as it turns out. So our LSM implementation on sort of local file system isn't entirely sequential writes. So what we've been doing is first changing it to be entirely sequential writes and seeing a little bit of performance benefit in local storage, about 10% improvement. Not a huge improvement because we weren't cheating a lot. Things like metadata were getting written in the wrong times. And now we're going to put it on HDFS.
Any more short clarifying questions? Yes?
What is the animal on *DB?
Oh, okay, yes. So that is a hyrax. And so the history of that, I don't have the right slide here for that. A hyrax is a small furry creature that's sort of a desert rock kind of creature. If you look in Wikipedia, you'll discover it's the closest associate, like genetically, of the elephant, right? So it's like a little furry, cute elephant. And they come in clusters. And so we're saying we're doing something other than the Hadoop elephant. And so we have these small, furry, cute things. And why would you not want a cluster of those instead of a big yellow elephant, right? So that's a hyrax. Check it out.
This will surely be a Trivial Pursuit question later.
Exactly. And we misspell it because it's also, sort of racks, as in racks of computers. And also hyrax was taken as an open source name by another project. So.
Okay, let's give Mike another round of applause before we bring him up for the panel session.